So I was so excited as I was going through and talking about all these different ways of factoring. There are so many other ways you can solve polynomials as well. So I do want to go over that really quickly before I start doing some of these practice problems here, which I'm sorry, they're kind of a little bit blurry. And I kind of don't have any more room on the back or on the front of this. So there's some other ways to solve polynomials. Let me make sure you can see what I'm doing. Here we go. Now, if you're unable to factor, that's what I didn't get at. Like, factoring is definitely the best way to solve if you're able to. But if you're not able to factor, then you have to have other ways to solve as well. So again, remember, solving means to find the x-intercepts. So another way to do it is potentially if they give you one factor, or if you know one factor already, you can divide that out. So we can divide out factors or x-intercepts or solutions already known. So this isn't ideal either. Oh, my pen's running out. Because if I don't already know one, then that's not ideal either. But I do want to talk about division. So there is long division, which, for example, would be something like I'm taking the factor x minus 2 and then dividing it out of x to the third minus 2x squared plus 5x minus 10. And like we're just straight up doing long division. So I'm thinking, like, how many times does this go into that? And it's x squared times. And then I have to multiply this by all of that. So x to the third minus 2x squared. And then we have to subtract everything. So double subtraction makes that a plus. And so we're left with 0 here, 0 there. And so I just drop this stuff down. And I'm thinking, how many times will this go into that? And like this divided by that is just 5, so 5 times. So 5 times each of these is going to be 5x minus 10, which when I subtract everything, it leaves me with a remainder of 0, which that tells me that this is a factor of that. And so when I write it out in factored form, I got x minus 2, x squared plus 5. And then I know one solution is 2, and maybe I do the quadratic formula over here or just solve for x. But that's kind of a long process. So if I don't want to do long division, there's also synthetic division, which is similar. So like if I take this same problem, I can synthetically divide it by actually, instead of using the x minus 2, I use that answer, which would be 2. And I just flip my division box upside down, because this is upside down dividing. It's synthetic is fake. It's fake division. So take this box, flip it upside down. And then I take the number I'm dividing it out of. And I don't take all the x's. I just take their coefficients, the numbers in front. So 1, -2, 5, and -10. And if there was anything missing here, like if that x squared wasn't there, I would need to put like a 0 placeholder for that x squared that was missing. So like you need all of the exponents represented, 3, 2, 1, none. And if you're missing anything, you need to have a 0 placeholder. And then the process goes, we drop down the first number, multiply the outside numbers, put it inside, and then add. Multiply, and then add. Multiply, and then add. My last number is my remainder, which we knew we had a remainder of 0. And then the numbers left over are the coefficients of my answers with x's behind them starting 1 degree less. So this was an x to the third, which means that this one is going to be an x squared, no x, 0x, and then no x on the 5. So 2, 1, none. And so I really don't need that 0x. You get your answer of x squared plus 5 next to that factor, which was x minus 2. And so you get the same thing. It's so cute. I love it. Now, again, division is still not ideal because I need to know a factor already, or I need to know an x-intercept already. And if they don't give me one, or I can't see one from a graph or something, then your real only other option after that is to use the, God, what is it called? The rational root theorem. It took me a second. Rational root theorem. It's not important to know the name. What is important is to understand what it does for you. So if you have a polynomial, x to the third minus 2x squared plus 5x minus 10, that same guy from before, if I don't know a factor of it, like I didn't know that x minus 2 is into it, you can find all of your possible factors or rational factors, because it might not have real factors, or it might have irrational factors, and you can't find those, but you can find rational factors, so nice number factors, by taking the constant factors and dividing them by the leading coefficient factors. And so the constant is 10. The leading coefficient is 1, but its factors are the numbers that multiply up to that. So like factors of 10 are 1 and 10, 2 and 5. And the factors of 1 are 1, and that's it. And then you have to like divide out each of them. So dividing each of these by 1 is not that interesting, but if you also had like a factor of 2 down here, then you'd have to also divide each of them by 2, which doubles the possible factors that you have. Also, they could be positive or negatives of any of those. So once you kind of know that your possible factors are plus or minus 1, 2, 5, and 10, then the quickest way to find one is to then synthetically divide until I find one with a remainder of 0. So synthetically divide until one gets you a remainder of 0. So I could go through and divide by 1 and by -1 and 2 and by -2 and 5 and -5 and 10 and -10. But the only one that's going to give me a remainder of 0 is 2, because I know that that's an answer. And when I divide that out, I would have gotten this. And truly, those answers there, when I set this equal to 0, I don't really need to use a quadratic formula. I can just subtract the 5 and square root. These answers are plus or minus I root 5. So they're not even real. And they're not rational, because the square root of 5 is a really nasty, yucky number. So you wouldn't have been able to find these ones because they're not real or rational, but you can find that 2 because it is real and rational, and it's in your little list down here. Oh my gosh, it's so fun. Okay, anyways, let's try some practice problems. That's a name. Is graphing the quadratic equation y equals x squared minus 8x minus 48. He substitutes 0 for x and finds that the y-intercept of the graph is -48. I thought that said neat. I was like, yeah, I agree. That is neat. I didn't need to do all that. It's just the last number. Next, he wants to plot the x-intercepts of the graph, so he rewrites the equation in a different form. Assuming he rewrote the equation correctly, the equation reveals the x-intercepts. Which of the following is the new equation? So if I want to see the x-intercepts, that was that factored form. So really, I just need to think about factoring this. Because once I'm in factored form, then I can see the x-intercepts, or I can see my answers. And so definitely the first two options are out because those are in vertex form. So I just really need to know how to factor this correctly. So I'm thinking what multiplies to -48 and adds to -8. And then I think too about like multiple choices. You can kind of see like those will multiply to -48, but adds to -2. So not what I want. These two will multiply to -48 and add to -8, which is what I want. So I kind of don't have to think about it too hard. Unless you get something like this and then you have to grid them in, because you do have these little gridded answers. So let's try something like that. If x squared plus 10x minus 24 and x is, oh no, equals. See, this little thing got goofed up. And then x is greater than 0. What is the value of x plus 5? Interesting. So I need to know what x is so I can plug it in and figure out what x plus 5 is. This x greater than 0 thing I think is important, but not yet. So if I want to solve for x, the fastest way to do it is to factor. But no matter how I do it, I have to be equal to 0 first if I want to solve for x. So solving quadratics or solving polynomials, you have to be equal to 0 first. And so I would try to factor this and think what's going to multiply to negative 24 and add to 10. And I think I want 12 and 2 because I need something to be negative and get 10. The 6 and 4 will get me 10, but they both need to be positive, and that won't get me the negative 24. So we got x plus 12, x minus 2, which means my answers are just negative 12 and 2. So that can be confusing because which one am I supposed to add to 5? And that's what this is telling you. X needs to be greater than 0, and negative 12 is not. So 2 is the one that they want me to pick and add with the 5, so 7. And when you're gridding these in, you always want to start at this like rightmost spot and write your number out that way. So it's just 7, and then we grid in the 7. Alrighty. I think I'm going to skip that third one. Oh, let's jump down to 4. That's interesting. What is the range of the quadratic function whose equation is So that guy is in vertex form, and I am such a visual person that I always like to give it a little sketcheroo. So because it's in vertex form, I can see the vertex. It's negative 4, 3. So negative 4, 3 puts me about here. And the negative tells me that the parabola is pointing down. So kind of like this. It doesn't have to be a super duper sketch, but that gives me an idea of what my quadratic looks like. And that's helpful because range tells me all the y values that this graph is covering. So this graph is not covering any of the y values up here, but all of them down there, because arrows mean go forever. So kind of the range or the y values of this graph start this high and go forever lower. So the y values are forever less. And it's also equal at this spot here, which is exactly 3 high, because again, that vertex was at negative 4, 3, so that y value is 3 high. So that's the one we want, B. Number 5 here is kind of similar to 2, so I'm going to skip that. Again, I just want to leave some for you guys to try, and there's not as many examples on this one, I feel. Okay, we could try this one. The graph of y equals ax squared plus bx plus c passes through these points. If the maximum value of y occurs at x equals 5, through what other point must the graph of y pass? So again, I'm a very visual person. I'm totally going to graph these out. So we got 1, comma, negative 8, and then 2, comma, negative 1, and then 3, comma, 4, and then 5, 1, 2, 3, 5, comma, 8. That's weird because this is a quadratic and it's not looking super quadratic-y to me, but if the maximum value occurs at x equals 5, oh, I see. Okay, so this is the max. That must mean that this is my parabola going down over here, and on the other side, I did a bad job. Like it repeats itself over here because it's symmetric. If that's your max value, it's a lot like a graph like this one was down here. So all these points just flip over. So I want to be on the other side of 5. So it definitely can't be that first one, but maybe it's at 6, 4. Was this 4 high? Yeah. Oh my God. Wait, is it 1 away though? Because it has to be equidistant away. This point here was at 3, 4, and this one's at 5, 8. So this is 2 away. So, and then 6 is not 2 away. So I think not that one. This point here, because again, it always has to be equidistant away. This point was what, 2, -1. So that's like 3 away. So if I go 3 away on the other side of 5, that's 8. And it has to be at the same height. Oh my God, that's 1. Yay. Okay. Kind of wild. Ooh, I'm just going to talk really quick about 7. The moment I saw 7, I was like, oop, quadratic formula. I can tell because of how the answers are written. So just quadratic formula that boy. We're going to skip that one for now. I'm going to skip 8 as well. And then I'm going to skip 9 as well. I'm sorry I'm skipping so many. But again, guys, there's not as many examples on this one. Let's try this long story problem one. All 50 states have legislation regarding pool safety, the majority of which includes a requirement for a safety fence around the perimeter of the top of an in-ground pool. If a rectangular in-ground pool has a length that is 2 feet less than twice its width, and then that's the width, and the area of the top of the pool, just the top, so area, like how much space it covers just on the top, is 480 square feet, how many linear feet of fencing are required, assuming that the fence is placed 1 foot from the edge of the water on all sides? Okay, we'll come back to that last part for the fencing, but I noticed right off the bat here that I can, obviously, hopefully you guys were understanding how I was writing these little formulas. They told me that the length was going to be 2 less than twice the width. And then this is just the width. And that's helpful because then they tell me the area. So I can find the area by multiplying length times width, and it will equal 480. And I do kind of want to times this out here. So like I'll distribute the W and we'll have 2W squared minus 2W, which makes this a quadratic that if I want to solve, I need to be equal to 0. So subtract that 480 over. Now, when I'm going to try to factor this one, because that's the fastest way to solve, I need to take out this common factor that they all have. Like they're all divisible by 2. I just want to divide that 2 out. So I'm dealing with smaller numbers, and it makes factoring much easier. So minus 240. And then we're thinking, well, multiplies to negative 240 and adds to negative 1. So that means I have to be really close together numbers. Oh my gosh, this is big. Like, I was initially thinking 24 because 24 and 10 is really easily, but those numbers are too far apart to get me just 1. I need the numbers to be really close together. So I feel like I need to walk it down from 24 and maybe try 20. Will 20 go into that? 240 divided by 20? 20 and 12? That's still too far apart. Walk it down. Maybe 18 goes into it. 24 divided by 18. No, it doesn't. 240 divided by 16. 16 and 15. 16 times 15 is 240. If I make this 16 negative, it'll still be negative 240, and it'll give me the negative 1 that I need. Yes. So we'll have W minus 16, W plus 15, which means that my two answers are 16 and negative 15, which probably doesn't make sense because we're dealing with real life things. It can't have a negative width. So the width here is 16. The length would be 2 less than double that. So if I double it, it's 32, and 2 less will make it 30. Now back to the real question though. Assuming that the fence is placed 1 foot from the edge of the water on all sides, now I think I really need for it to be 18, because we would go a foot this way, a foot that way. And I really need it to be 32 because I need to go a foot that way and a foot that way. So 32 and 18, and we want to find fencing, which is not area, that's perimeter. So I want to add it all up. So I mean, you could do it the hard way and do 32 plus 8, or 32 plus 32, 18 plus 18. But I think actually adding these two for 50 and then doubling it, because there'll be another of those over here, is the easiest way to go. Oh my God, all of that, and it was just 100. Maybe there's a faster way that you guys know. Okay, 11 looks really good, but I think I'm going to save it. Let's jump down to 12. Gosh, I almost want to save that one for when we do geometry stuff. Which of the following equations could be used to represent the area of the trapezoid? Well, I mean, there is an area formula for trapezoid that I think they might give to you, but you could also think of it as a square plus a triangle. So the square, is that k plus 1, I think? I guess it's not really a square, it's a rectangle. But the area of that would be like the height here, which is k plus 1, times the length here, which is k. And then I would need to find the area of the triangle, which is half base times height, which this is like your base and height, anything that's perpendicular. So from k to 2k, that's just k. And then times the height, which is still k plus 1. And so then we want to add those two together, which, I mean, let's maybe simplify them a little bit. We'll have k times k, so k squared plus k. And then here, I kind of have to distribute one at a time, or I feel like I want to at least. So we'll have half, and then k times k, so k squared, and then k times 1, so k. And then I want to take half of each of those. So really just k squared over 2 plus k over 2. And then I have to add that to this. So k squared plus k squared over 2 plus k over 2. If I want to add up fractional things with non-fractional things, I need to have a common denominator. So I'm really going to make this 4 over 2. No, 2 over 2. I'm dumb because it's 1. 2 over 2 and 2 over 2. Then add up my like terms here. So we'll have 2k squared plus k squared, which is 3k squared over 2 plus 3k over 2, which is this one. They're just writing it as one big old fraction. Cute. Polynomial land, let's go there. So 13, I'm going to get interrupted by a bell. I'm so sorry. If a function p of x has 4 distinct zeros, which of the following could represent the entire graph of p in a standard coordinate plane? So having 4 distinct zeros just means has 4 x-intercepts that are all different. So this only has 2, this only has 2. This has 3, but kind of 4, but that fourth one is the same right there because it's a bounce. This one has 4 distinct, so D. Let's see. Ooh, here's a dividey one, a remainder one. Oh my word, these are all so good, but I feel like I gotta make a pause here just because of that bell. I'm so sorry. I'll make another short video.